Hello and welcome to our presentation titled Urbanet, Leveraging Urban Maps for Long-Range 3D Object Detection, authored by Juan Carrillo and Professor Stephen Waslander, and presented at the International Conference on Intelligent Transportation. The motivation for our study is twofold. First, we would like to contribute to improve traffic safety. In Canada, 30% of fatalities and 40% of serious injuries happen at intersections. And that statistic, it's about 40% in the United States. In terms of vehicle flow, being able to monitor vehicles as they approach and move through intersections will help reduce traffic delays and improve traffic flow. The problem definition is how do we accomplish long-range 3D vehicle detection using a single traffic camera? By detection, we mean determining the size and pose of the vehicles. And since the camera has a higher viewpoint compared to cameras on board vehicles, we need to account for rotations of the 3D bounding box, which means these boxes don't have or will have a pitch value. The metric we use to evaluate our models are average precision. Getting into more details about the problem definition, the reference frames of the map and the sensor frame are not aligned. That's why we need to account for the rotation of the 3D bounding boxes due to changes in perspective as well as changes in the slope of the road. In terms of challenges and previous work, we know that the output of sensors degrades with distance. For instance, in cameras, objects that are far away appear smaller and are represented by fewer pixels. In LiDAR, we have fewer return points per each object, which means there is a more sparse point cloud. And when it comes to radar, we also have a significant sparsity in the returns of the signal. Ranging sensors like LiDAR or radar are also more expensive, which difficults their implementation at many intersections. And another alternative, which is using stereo cameras, is not as accurate as the other sensors, or stereo cameras are more accurate at closer range. In terms of previous methods, the methods published in the literature focus more on vehicles that are closer to the intersection and only on detecting vehicles in 2D or counting vehicles as they pass through an intersection. The papers we see in the literature are also mainly focused on applications for autonomous vehicles and less about intelligent transportation systems. Getting into more details about our method, we introduce the idea of having a 3D object descriptor in this method. This object descriptor works by inferring the location of 9 key points as they are projected onto the image, along with the size of the object, in this case the vehicles, and the observation angle. These figures show what are the 9 key points. Key point number 9 is the centroid of the vehicle, and it is not drawn here to avoid cluttering the figure. Now, the method we introduce in this paper is called Urbanet. We start with an image collected by a traffic camera. We run a 2D object detector, a mature 2D object detector, to get tight 2D bounding boxes for each vehicle. We also have a map of the center of the driving lanes on the scene, and we use these 2D bounding boxes to crop the projection of the driving lanes onto the image plane. We then concatenate the image snippet that comes from the camera, as well as the additional channel that represents the driving lanes, and feed it into a 3D object descriptor. This model in turn outputs a vector encoding that includes the 9 key points in image coordinates, as well as the size and observation angle of each vehicle. These 9 key points are normalized in a range from 0 to 1 using the width of the image snippet to scale the values. We also have the elevation and slope of the scene in map coordinates, and from there we extract the geometry of the local plane that is right below the vehicle. The combination of the driving lanes along with the elevation and slope make the urban 3D map. Then, by using projective geometry, we clamp this 3D bounding box into the road by back projecting the key points into the 3D surface in order to determine the size and pose of each vehicle. The dataset we use for our experiments is synthetic data generated with the GTA 5 video game engine. Here we have the simulation of long-range traffic cameras at 7 intersections, and these images correspond to high-resolution 4K images collected at 10 Hz. The labels include the 2D and 3D bounding boxes of each vehicle, as well as the center of driving lanes and the digital elevation model. These are additional data inputs that we have available for our experiments. The figure on the right shows the projection of the centroids of the training dataset into the 3D surface of the road, and we show how the vehicles follow the patterns of the driver lanes. That's why we consider that this center of the driver lanes, it's an important variable to consider. Now, when it comes to the train and test splits for training, we use 5 viewpoints. As you can see, we have cameras looking at roads with changes in slope, changes in perspective, different view angles. And for the test, we have 2 different viewpoints that do not overlap with the training set. This is the count of vehicles in the train and test splits. Most of the vehicles are in the range from 50 to 140 meters. In terms of the experiments, for the 3D object descriptor, we use a simplified BGG style network with about 700,000 parameters, which is a fairly small model and is therefore efficient for running on edge devices. The training of the 3D object descriptor, it's done by using the Atom optimizer. We train for 120 epochs, and we use an NVIDIA GeForce RTX 2080 GPU. As for the results, we run multiple experiments. Let's start with the legend on the left, which describes what is the meaning of each color. So one of the experiments we run, it's by using the elevation map as it is originally. We also introduce random noise that it's in the range from 0 to 10 centimeters in elevation. It could be, it's in the range from -10 to +10 centimeters. And we also have another variation in terms of noise that goes from -40 to +40 centimeters in the elevation map. We also have variations including driving lanes and without including driving lanes. So the figures on the right, the top right figure shows the results of the mean 3D intersection over union across range when using the driving lanes, using all of the 9 key points, and that gives us a mean 3D IOU of 0.59. The figure on the center right corresponds to the experiments without using the driving lanes, and using all of the key points we can see a reduction in the performance of the model. That means the driving lanes certainly contribute as a prior to help improve the effectiveness of the 3D object descriptor. And the figure in the bottom right shows an experiment where we do use the driving lanes, but we only use the key points at the bottom of the bounding box for the 3D object descriptor. That means key points number 1, 2, 3, and 4, which is the minimum we need in order to clamp that 3D bounding box into the road surface. As we could see, the performance degrades as well compared to the nominal conditions on the figure on the top. And in all the experiments, you could see in the colors that the map that uses the nominal elevation always gives better results, and as we increase the random noise in the elevation map, we get degradation in the effectiveness of the method. We also evaluate the method using 3D mean average precision in bird's eye view, using a threshold of 0.5 for IOU, 3D IOU, and 40 recall positions. This table summarizes the results. The first row corresponds to UrbaNet, nominal UrbaNet. That means using the driving center less and using all of the key points. And the following 2 rows shows the results when we run the ablation experiments, when we ignore the driving center lines, and then when we use only the key points at the bottom of the 3D bounding box. The columns represent different levels of noise in the elevation map. These are some examples of vehicles as they are detected at multiple ranges. So ground truth, it's bounding boxes in green, and predicted, it's bounding boxes in red. As for the conclusions, we introduce Urbanet and show that using driving lanes as priors improves 3D characterization. We also show that deep learning and 3D maps is an effective combination to determine accurate 3D pose, and that our method generalizes well to unseen viewpoints. This research was partially funded by Huawei Canada. Thank you very much.